each specific component of the resulting vector inside. So, once you write down this weight matrix and these vectors as their own symbols, you can communicate the full transition of activations from one layer to the next in an extremely tight and neat little expression. And this makes the relevant code both a lot simpler and a lot faster, since many libraries optimize the heck out of matrix multiplication. Remember how earlier I said these neurons are simply things that hold numbers? Well, of course, the specific numbers that they hold depends on the image you feed in. So it's actually more accurate to think of each neuron as a function, one that takes in the outputs of all the neurons in the previous layer and spits out a number between 0 and 1. Really, the entire network is just a function, one that takes in 784 numbers as an input and spits out 10 numbers as an output. It's an absurdly complicated function, one that involves 13,000 parameters in the forms of these weights and biases that pick up on certain patterns, and which involves iterating many matrix vector products and the sigmoid squishification function. But it's just a function nonetheless. And in a way, it's kind of reassuring that it looks complicated. I mean, if it were any simpler, what hope would we have that it could take on the challenge of recognizing digits? And how does it take on that challenge? How does this network learn the appropriate weights and biases just by looking at data? Well, that's what I'll show in the next video. And I'll also dig a little more into what this particular network we're seeing is really doing.
Hi, sir, we can't hear you.
Not sure. I'm not sure what's happening.
We can now hear
Can
you.
you guys hear me?
We can hear you now.
Okay, thank you very much. All right, so, but were you guys able to hear the sound of the video?
Yes.
We heard the video.
Okay, perfect, perfect. Any question on that video? Anything that you, anything that confused you when you were watching the video? Any misunderstanding? Anything you never understood? Any question on that, guys?
I have a question.
Yeah.
Is the sigmoid function the only function that's recommended on the output?
Okay, so we will, when we talk about activation function, then we're going to talk about different type of functions such as the sigmoid function, softmax function, ReLU function. So it's mostly okay. Think about it this way: when you're looking at the neural network, right? So because the model is going to be changing all this weight, and then we, as the value goes to the next layer, we don't want it to get to a point where the numbers or the value is growing, right? To a point where we cannot control it. So we want to keep it in a certain range. So that's why we use activation functions. So we will see when we learn about activation function, you will see what's the difference between activation function, and you will see why certain functions such as sigmoid functions, you cannot just add them anyway in the network, or else it's going to make your model inaccurate, right? So and then you have functions such as ReLU. The ReLU function, activation function, you will see it's the most used activation function when it comes to uh, use activation function, because of the fact that it doesn't have what we're gonna learn about, which is called the gradient explosion, or the any type of issue with the gradient. But we're going to talk about that because we have a vanishing gradient that can happen during the learning process. And to avoid that, you have to make sure you choose the right activation function. But when it comes to the last layer, after the last layer, there's such activation function, because the last layer needs to be an activation function that determine the output. So if we're dealing with a classification problem, the last layer you need to use a softmax function. Because the softmax function, whatever output, whatever information was coming from here, it's going to turn that information, convert it into a value between 0 and 1. And that will determine if you're going to go with option 1 or option 2. Let's say you were dealing with a model where you have to determine between male and female, right? Where you say everything above 5 is female, below 5 is male, things like that. Okay, did I answer the question, or is there any other question?
You answered it perfectly. Thank you.
All right. Okay, so guys, so that's how neural network work, as you've seen it in that video. So basically, when we're training our model, each sample will be taken into the network. So each sample will be divided into input data. So the network is going to process each sample and find a certain pattern until it finishes all the samples that you have in your data set, and it creates the final model. That's how a neural network will work. Okay, so remember when we spoke about machine learning, we say, because we need to reduce the loss. What is the loss? Is the cost. What is the cost? Is the difference between the value that we're trying to obtain and what we are obtaining. So it's the inaccuracy of the model. So the loss is also called the error. So we will have the loss function, which we also call the error function. So you will need to understand that during the training, when we're trying to target a certain value or a certain function, we can't reach what we're trying to target. So we have a loss function that we can measure there. And the loss function that we use, we need to make sure that in that loss function, when we use the loss function, it needs to give us a value that is as low as we can. That's how we're training the model. Okay, so the loss function which we have here. This is an example of a loss function. So the loss function will actually reflect the error between the target output and the actual output. Okay, so when we're using what we call a perceptron, when we're using something with just one training sample, when we use that, a loss function that we can use is a quadratic cost function, which is represented like this. So, and then this function, the TD here represents the target output that we want to get. The OD represents the actual output that we are getting. Okay, so we take the target output minus the actual output, right? And D here is the number of layers in the output layer. Okay. And the small d would be one of the neurons in the output layer. So we have this, but we don't have to memorize the formula or really know the formula, because when you're doing it in programming, when you're coding, you just have to know which loss function to use, and then you're going to call it. You're just going to write the function there by writing a certain word or a certain syntax, as we call it in programming. Okay, so the gradient descent method. Remember when we did machine learning, we learned that the gradient descent method is one of the methods used in machine learning to try and reduce, to try and enable the loss function to search along the negative gradient direction and update parameters to minimize the loss. So that's the gradient descent. Okay, remember we said when we have the gradient descent, so this is an example. This is the function that we have. So it's going to be taking wherever we have the weights that we're using there. So it's changing the values of the weight until we can get the weight that gives us the smallest loss. Okay, so the purpose of the gradient descent is just to reduce the loss. Okay, so common loss function in deep learning. The loss function will also depend on what problem you are solving, you know, what type of scenario you're having. So we have the quadratic cost function, or the quadratic loss function, and we have the cross entropy error function. So you can see it's different functions here. So depending on the problem we're solving, so if we're dealing with a classification problem, okay, so if we're dealing with a classification problem, we use the cross entropy. Remember what I said, the most important thing we need to always ask ourselves is what problem are we solving? So if the type of scenario that you're solving is a classification problem, you need to use the cross entropy error function. Okay, so now when we have a regression problem, we use the quadratic cost function, which is also called mean square error function. Okay. Okay, so remember we learned about three types of gradient descent. We had the batch gradient descent, the mini batch gradient descent, and the stochastic gradient descent. I hope you remember that. So does anyone remember what's the difference again, or any of them? What is the batch gradient descent? What's the difference between the batch gradient descent and stochastic, or stochastic and mini batch gradient descent? Any of them? Does anyone remember anything? We spoke about it when we were doing machine learning. Anyone remember? Anyone? And does anyone remember what's the difference between this gradient descent? I need just one person to remember. Okay, so it seems like everyone forgot. All right. So the difference is just in the word itself. So the back gradient descent, remember the whole gradient descent is all, this method is all about letting the machine keep changing the weight. So we're going to initialize the weight. So we keep changing the weight until we reach a certain accuracy of the model. So with the back gradient descent, if you have, so each sample, so if you have 5,000, so for each sample will be recorded as X and T. So the X represents what? It represents the input vector. So the input vector means that all the information about the input. So an input vector can be something like, let's say in your input, in your model, you trying to check the age and the weight of the person. So these two values will represent a vector here. Maybe the person is 16, the weight is 50. So this is a vector, this is an input vector that we have. And then the output, we just want if the person is healthy, yes or no. So the output target will be represented by T, and the input vector will be represented by X. So each sample will be recorded with this information. And in a back gradient descent, so every time we change the weight, now remember, now I'm not talking about this weight as this feature here. I'm talking about the weight and the weight in machine learning, the weight here. So every time we change the weight, we're going to change the weight for everything, for all the samples at the same time. So in the back gradient descent, we take the whole batch, the whole data set, we change at the same time, right? But in the stochastic gradient descent, we're going to be changing this weight for each sample at a time. So we're going to be updating each sample at a time. We're not taking the whole data set. So we're only taking one at a time. And the third one will be the mini batch gradient descent. The mini batch gradient descent, this one, we're going to take a group of samples. Not one, not the whole data set, but we're going to take a certain group. And then we update the weight at the same time for that group only. All right. So when we talk about back propagation, so when we talk about back propagation algorithm is when, because remember, information are sent in a forward direction. So basically we have the input layer. So all information move from the input layer toward the output layer. But a back propagation algorithm is when we're trying to find the error. So the way the machine would work to try and find the error and see where the cost is, where the error is, it goes in a backward direction or back propagation direction. Okay, so the loss function here, when we're operating it, when we're gonna go backward. Right, so these are example of how the errors are represented. For example, here you can calculate the error, and here we can calculate the error that are accumulated in the whole neural network in either layers, and then we have the error which is accumulated from the input layer. So all these formulas are transformed into programming code. Okay, so these are just back propagation algorithm. All right, so now we have activation function, which we spoke about it. Forgot who was that. Forgot who asked. I don't know. I think it's not Hundo. I'm not sure who asked again. Okay, so activation function. So activation function are just a mathematical function that I use in AI to transform the output into a certain form. So what does it mean? So what it means is that we want to transform whatever output we have into a certain range of data that we want. So an activation function is very important in neural network. Okay, so an activation function will allow us to introduce the non-linear features to the network. So without the activation function, the output signals are only simple linear function. So when we look at it, we think, so basically, if we're trying, for example, to determine between mangoes, bananas, apples, so you have a classification problem where we're trying to get a certain probability of something being a banana or being a mango or anything like that. So the last layer, we're going to have an activation function, which will turn that whatever function we get, whatever information we get, will turn it into that probability of a value between 0 and 1. So we can have maybe 0.55 value. So the function that allows us to do that is an activation function. And sometimes we have an activation function that we can use as well in between layers. So we want from the first layer or the second layer to the third layer, we want to have a certain amount, a certain type of data. We can do that. So there's different type of activation function, and it is very, very important for you to really understand what type of activation function you are actually using, because if you use the wrong activation function, you're going to create an issue with your model. It may lose its accuracy or it may not perform as you want. So it's very important to really understand the type of function that you are using. All right. So the first one that we're going to see will be the sigmoid function. So the sigmoid function, what it's going to do. Okay, so first of all, the sigmoid is represented by this. So this is the formula behind the sigmoid function. Okay, so this function is also known as a logistic function. They can also call it logistic function. Logistic. Okay, so it can also be called a logistic function. And what it does is that it's going to take whatever value it gets, take the function. This function will map. It's going to map the values, right? It's going to map the any real value number into a number between 0 and 1. So 1, we have 0 here. So between 0 and 1. So whatever we're going to get, it's change it into a value between 0 and 1. Okay, so I remember as I told you about the example of the probability that we're trying to get for when we're dealing with a classification problem. Okay, so we need to note that when you look at this, this is not a linear function. That's why it introduced a non-linear function into a linear. Okay, so we want to have this turn any value that will come, it's going to turn it into a value between 0 and 1. But one of the most dangerous problem with sigmoid, if you're using sigmoid, the more layers you're having, you're going to have an issue called a vanishing gradient. And this is not a good thing for machine learning. Okay, so when we have a vanishing gradient problem, it is very, very dangerous. So we don't want to have that. Okay, so the next one will be the 10H. So the 10H is also an activation function, which is represented by this formula here. Okay, so the 10H just stands for hyperbolic tangent. So this is also a mathematical formula, and the 10H, the way the 10H will work is that it's going to take the function, going to take the value and in between a value. So the range will be between -1 and 1. And this is the formula. Does it have a vanishing gradient problem? Yes, it does. So the 10H will also give us a vanishing gradient as we going through multiple layers of in our network. So the bigger our network is, the more we're going to have a vanishing gradient problem, which is created by the 10H. Okay. So remember, 10H I use as well in deep learning. But if you have a very you don't have a deep neural network, you can still use the 10H without any problem. But as soon as you have so many layers, it's better to stay away from the 10H. Okay, so and then the next one will be the soft sign, right? Excuse me. So the soft sign will be also an activation function. It's represented by this here. Guys, what does this mean? When you have an X with those two bars, what does it mean? When you have that in mathematics, what does it mean? What does it mean, guys?
I don't know if I'm correct, but I think they are called absolute values. I think X is either negative or positive.
Yes, you're right. So that stands for absolute value. It means the value has to be positive. All right. So whatever value you get there, it has to be positive. Okay, that's right. So you can't have a negative number here. So what it's gonna do, whatever number you're having, it's gonna make sure it makes the number positive. All right. So the soft sign is also an activation function, and the soft sign also take any real value and turn it into a value between -1 and 1. It also has a gradient vanishing problem. And then we have the third one, which is the rectifier linear unit, or also called the ReLU. So the ReLU is the best option. Why is the best option? Because the ReLU does not have a vanishing gradient. So no matter how big your neural network is, you're not going to have an issue with that. So that's the advantage. That's why the ReLU is most used into neural network when the network is really, really, really deep. Okay, so so the ReLU, what the ReLU will do is that any value then 0, and for any negative value, it's going to return 0. But for any positive value, it's going to return 1. Okay, so that's it. So the ReLU will be used into the neural network for the advantage of not having a vanishing gradient problem. Okay, so and then the other one is a soft plus, which is represented like this, which also has a vanishing gradient problem, right? So, and then we're looking at the soft plus, the fact that the soft plus also have a vanishing gradient problem, so you also have to be very, very, very careful, okay? So it's kind of similar to the review in terms of whenever there is a positive value, it's going to also return a positive value, but it go in an exponential way, right? So it's closer to the review. Okay. Okay, so it's mostly used into issues that have to do with probabilities, you know, getting probabilities of something happening and things like that. But just be aware of the vanishing problem. And another activation will be the softmax function. This is the most used activation function when it comes to classification problem. When you're dealing with multi-class classification task, you use a softmax function. So this function is the one that will tell us if we are working on a scenario where we want to determine between let's say mangoes, then we have apples, we have oranges, you know. So if you want to determine between these, so the softmax function, what it's going to do is in the end, the softmax function will determine the probabilities of each. So the softmax function will help us give these three outputs. Let's say, for example, we have to do, it's going to give you maybe here, we have 0,24. Right, so we have 0,24 here, and then here it gives us maybe 0, maybe 35, and then here it's going to give us a 0, what is that? Maybe a 0,41 here. Okay, so you have this. This is done by the softmax. So the softmax will give us maybe 0,24 for the first one, for the mango, 0,35 for the orange, and 0,41 for the apple. Therefore, this fruit is an apple. Okay, because of that. So that's what the softmax function will do. All right. Okay, so that's the thing. So we have activation function, softmax, ReLU, 10, soft sign. Okay, so those are activation functions. And then the next thing will be the normalizers. So the normalizers, as you can hear the name, it's more about making things normal, right? What does it mean? So normalizers will help us to actually control, prevent every issues that can create an overfitting problem. Remember, what is an overfitting problem? Is when your model has been trained with an algorithm that is more advanced than the amount of data or the type of data that you are having. So now your model will perform well when you're training it, but it's going to perform bad in the real world. Okay, so regularization is important. So that's why we're going to use normalizers. So the regularization is important and effective technology to reduce generalization error. What is generalization error? Is the error that we get when we give the model new data that the model has never gone through. Okay, because sometimes you're going to be training with a certain type of data, and because the model has already been involved with those data, it's going to perform well. But when you bring new data, it's perform well. Okay, so because of this issue of generalization, what we're gonna end up having an overfitting problem due to large number of parameters. So therefore, to avoid that we use so many parameters that will give us an overfitting problem, we need to come up with normalizers. And what are normalizers? Normalizers are just methods that will help us avoid that. So we have a few methods. The first method will be to add a constraint parameter, such as the L1 and L2 norm. What does it mean? It means your weight. If you want to have a weight, instead of you having any type of weight, instead of your model to be updating any type of weight, you want the weight to just be between 0.5 and 1. You want to keep it in this range. Or you want to keep it below 3. So your weight must not exceed 3. So that will be, you will use a L1 and L2 constraint, which we're going to talk about tomorrow, right? Another option, another normalizer can be to just expand your training set. So if you're dealing with data and then you realize that, no, we're having a problem. You want to create a model to determine between dogs and cats, but out of 5,000 pictures, you have 4,000 pictures of dogs and only 1,000 pictures of cats. So that is a problem. So you will need to expand your training sets and create, maybe add more pictures of cat as well, so that the model can have enough pictures of each category and learn from it, right? Another example can be is to add noise. If you're dealing with something that has to do with sound, add background noise, let your model understand all those things, and you understand. So if you're dealing with pictures, you can transform the data by maybe changing direction of data, you understand? So things like that. All right, and then we have another method, which is a dropout. So a dropout is sometimes a certain part of the neural network is not important. We just have to cut the neural network and leave a certain part, okay? And another method can be an early stopping. Guys, all these things, when we learn Python programming, we're gonna learn what type of code do you write to apply a dropout. But you need to understand what is a dropout, what is an early stopping, so we know when to apply them. Okay, so an early stopping is when you're training your model, the error is reducing, and then you get to a certain point. Let's say, for example, you want to train your model 1,000 times. You've created a game. You want the game to play 1,000 times to understand. So you want the model to train 1,000 times. As you train the first time, you get this error here. This is the amount of error that you get. You train again, you get that. So the more you're training, the more the error is reducing. And then by number 500, your error is low here. But by the time you get to 600 times, your error starts increasing again. By the time you get to 1,000 times, you realize that you are somewhere here. And you're thinking that your model did not really train properly because the error did not really reduce from the beginning. But when you look during the process, there was a time where the error was really small. So you could have just stopped here. Instead of training 1,000 times, we can just train it 500 times. So this is an early stopping method. All right, guys. I think that's it for today. And tomorrow we're going to start and actually show what is the L1 and L2 constraint and expanding, and just go through this. All right, guys. Any question? Any question? In the meantime, we can turn on our cameras while trying to get questions from anyone who has a question. Any question, guys?
Hi, sir. My question is not related to AI, but it's related to like the big data exam.
Okay.
So my application for the voucher hasn't been approved yet, and I applied like last week on the 26th because my first application was rejected.
Okay,
And I
guys.
see.
Okay. Well, okay. When it comes to exam, any assistance, I think on the group there is the guy who's the ambassador. What's his name? Arif. You can speak to him, or you can also speak when you check in the admin. You'll find Pauline, so you can speak to Pauline as well.
Is Pauline on
Especially, yes, Pauline is on the group. She's on the group. When you check the list, the names of the admin, you're gonna find Pauline.
Okay, okay, thank you.
Yeah, so I'm sure every email that you receive is coming from Pauline. So Pauline is the right person to assist you with regard to exams.
Okay, thank you.
All right. Thank you very much, guys. All right, guys. I guess I will see you tomorrow. Okay. Have a great evening.